Melko.
Thank you. Thank you very much. Okay. On Friday, I tortured you guys with algorithms for classical Monte Carlo. And what we were doing is building up sort of some intuition for the quantum case. And so today we're going to talk about quantum Monte Carlo. And specifically, strategies for simulating spin liquid states in quantum Hamiltonians. So, unlike the sort of classical analogs or classical, I guess, states which were highly degenerate that I talked about last time, like spin ice and the Z2 gauge theories. Today we're going to talk about the actual real quantum spin liquids. And strategies including basically how we construct or how we think about constructing updates in the Monte Carlo algorithm. So a few things we're going to talk about are what types of spin liquids, I guess, are possible, or how do we go to construct a quantum Monte Carlo to look at a spin liquid. And there's many different people might have many different models that they're interested in. There's actually a whole zoo of algorithms called quantum Monte Carlo, and you might have there might be a different algorithm suited for different problems. So the first thing is to recognize that I guess there's a whole zoo of QMC techniques, and depending on the problem of interest, whether you're looking at maybe you want to look at something like the toric code Hamiltonian, or you might look at something like quantum spin ice, something maybe derived a little bit more or connected a little bit more closely to experiment. You might want to look at a wave function, so just a sort of a resonating valence bond wave function or something like that. All of these have different configurations, different constructions for their configurations, which I'll talk about, which we identified last time. And they also have different updates and different ways of constructing algorithms. So there's actually a huge amount of, I guess, literature on this, and a lot of people work on different types of algorithms. So I won't be able to sort of cover all of these zoo of techniques exhaustively, but I will give a bit of a flavor for the strategies I think you need if you're going to study spin liquids in a pretty large subset of these zoo of techniques. What unifies all things QMC, or almost all things QMC, I would say are two properties. One would be the fact that your configurations, which I'll talk about again in a second, the things that you're sampling, the things that you're updating, the classical representation, if you will, of maybe your partition function for a finite temperature simulation. So these are d plus 1 dimensional. So the picture you should have in your mind is sort of a path integral picture. The idea that somehow on your conventional classical computer, you might have a d-dimensional, I just drew it as a one-dimensional, but a d-dimensional, say, basis state, or the spatial degrees of freedom associated with the thing that you're studying. Might be spins, might be something more exotic like singlets, or like these entangled singlets or valence bonds. And you also have this extra dimension that you can imagine looks like you have something like world lines, perhaps, where you might trace, say, either, say, the spin 1/2 up of a spin, like an SZ basis state, or it could be the presence of a boson. So whatever this is, this extra dimension will typically identify with imaginary time, right? So if you derive your path integral, like you would do in, who knows, some class, I suppose, you'll remember that your path integral has this, you basically do some sort of time evolution, and it happens to be an imaginary time. So imag time. And that object that's your sort of, your spatial, I guess, representation of your basis, plus all the world lines or all the imaginary time evolution, that's the thing that you sample. That's your configuration. So unlike the simple classical case where, we mostly looked at spin systems, I guess, but you might have Ising degrees of freedom on a lattice. You construct updates of that configuration. That's the thing that you store in your computer, right? And so it's very intuitive and simple. You just do single spin flips, or we were talking about non-local updates for some of these sort of classical spin liquid states. Here you have to update the position of these world lines. Maybe how they, how the kinks look in these world lines, maybe how they wind, and so on. So that's a little bit less, I guess, sort of intuitive. And that's the first thing that we'll sort of derive today is a simple picture of how those world lines occur in something like a Heisenberg model. Okay, what am I talking about? So that's one, what I'd say, unifying property of what we call QMC. And the other thing is the presence in almost, and actually all of these different zoo of quantum Monte Carlo, world line methods like this, series expansions like all derive, variational methods, path integral methods in the continuum. What am I forgetting? Who knows? Determinantal Monte Carlo for like Hubbard models and so on. All of these in some form have a sign problem. And the sign problem is particularly important for the types of Hamiltonians that we often want to look at when we're searching for spin liquid phases. Okay, so the question of whether or not we can sort of generically simulate, I guess, frustrated spin models or bosons with frustrated hopping and all these interesting models that may or may not have spin liquid phases, oftentimes come down to whether or not there's something called a sign problem. And the sign problem is the existence of negative weights. Remember the weights we defined last time. So we'll talk about this now. The other thing I want to emphasize, which I might not get a lot of time for, is that in addition to the sign problem, the other thing that sort of impedes progress in simulating a lot of the models or Hamiltonians that we're interested in studying or searching for spin liquid phases is, again, updates in ergodicity. So even though we're gonna focus a lot on the sign problem, this whole idea that we discussed last time, the idea of local updates, non-local updates, ergodic sampling of maybe winding number sectors, or ergodic sampling of all these different states in this highly degenerate manifold in the classical case. We also have to worry about ergodicity now, but it's actually much more complicated because we're worrying about it in this d+1 dimensional sort of world line picture. So updates. And this idea of ergodicity is something that's often overlooked when we're constructing algorithms for the types of Hamiltonians we're interested in. Oftentimes we look at whether or not we have a sign problem and just say, okay, no sign problem, we can simulate this with quantum Monte Carlo. But we have to think about whether or not we can design updates that keep us ergodic in the space. And again, I will talk a little bit at the end about measurements. We also have to be aware of what types of measurements are possible with QMC. And there's many different types of measurements. You can do all these diagonal two-point correlation functions. You can do off-diagonal operators, correlation functions, and so on. I'll focus again on these Renyi entropies, and I'll introduce the quantum version of that classical Renyi entropy measurement that we talked about on Friday. Okay, so again, the goal in some broad sense is to calculate the expectation value of some operator. So in the quantum case, we're taking some trace, e to the minus beta h, where that's now an operator. And just like last time, we're writing this expectation value as a sum over configurations. I'll call them x again. The value of that operator in the configuration, and then some weight. And in the classical case, at finite temperature, I wrote the weight is essentially the Boltzmann weight, right? But in this case here, where we're looking at some sort of d plus one dimensional picture, it's not as obvious what that weight is going to be. And so the first thing you have to think about is, what's this weight? How do we take these weights and construct transition probabilities between different configurations that satisfy detailed balance? Okay. And again, just like in the classical case, we don't do a brute force sampling of all possible configuration x. Like, think of this being 1x, We might want to update this configuration by maybe moving this world line somehow. So we don't just brute force sample over all possible world line configurations when we do a Monte Carlo. This would be very inefficient, just like it's inefficient to sample, with equal weight all classical configurations of an Ising model. So what we do is we construct sampling according to this weight. We sample configurations based, predominantly on which ones are weighed higher. And once we have a sampling according to that weight, so which is importance sampling, then we just calculate the average value, or basically the running sum of the observable in a weightless way. So the same importance sampling philosophy that we had classically. Question? So x, there's different ways of constructing x. Pardon? This is like the partition function on the bottom. This is just one way of writing a partition function. And again, write the partition function as the sum over weights. Okay, yeah, I'll go through that all now. I'll show you exactly what this basis is and what I'm going to derive right now what the configuration is in some simple case. Okay.
Question. So right now you treat this beta, finite beta as another dimension. And will you comment that for zero temperature? Because sometimes we know dynamic exponent is not necessarily one. Dynamic exponent is not necessarily one.
So I don't know so I don't know exactly what the question was, but I can reformulate this exactly, or essentially as a zero temperature projector method. And the basic difference is, which I'm going to derive right now, is if you take this beta, this is your imaginary time, this is going to be your beta, your inverse temperature. If you take beta to infinity, you basically can do that. You can construct a QMC that samples that beta equals infinity simulation cell without actually defining any temperature. And you can just imagine projecting from the edges. So when this goes out to infinity, sort of the periodic boundary doesn't matter in some sense anymore. And you can also construct QMC schemes based on that. And you can construct configurations and so on. So I'll talk about that. Yeah. So let's keep beta for right now, and let's basically look at the expression for the partition function and derive weights in some simple case. Okay. So the method I'm going to, so the sort of derivation for these configurations that I'm going to go through now is like, it's like what I learned in grad school. I haven't learned anything since. It's called the stochastic series expansion algorithm that Anders Sandvik taught me. And the idea is to write a partition function, okay, which, I'll write as the diagonal matrix elements. So alpha is going to be some basis which I'm going to choose, some basis state. Importantly, because we're dealing with the finite temperature path integral, that comes in. That dictates that essentially this is this world line will be periodic to keep this matrix element as the way it's written. And I'm going to do a series expansion, hence the name, a Taylor expansion of the exponential. So I think I want to write this like, I think I have this written in the notes. So tell me if I'm making any mistakes. So what I've done is I've pulled out minus beta to the power n factorial. And I've written the formal h to the power n, which is the Hamiltonian operator, is n, product of n operators. And just like you said, just like when you derive the path integral, in the usual case, we'll insert resolutions of the identity in between each one of these powers here. So. And right away, this is what's defining our weights. Okay, so just like I said, we do importance sampling of configurations based on weights. Here we have a partition function z that I've written as a sum of weights. What's going to happen is each one of those wx is going to be sort of the terms that occur after these sums. So I have a bunch of resolutions of identity. I have to take all these sums and write them. So I'll just write them as a set. I still have this n from 0 to infinity. I have minus beta and n factorial. And then I'll label these. So now I have n of those matrix elements. And I guess the last one's alpha n minus 1 h alpha n. And again, this alpha n has to be, this basis state has to be equal to alpha naught. So what happens in Monte Carlo, so just like in the classical case, I have a sum over configurations. So I can imagine somehow, sampling, both the basis states, all these alphas, right? And I can imagine sampling, terms in the Hamiltonian that do this type of d plus 1 dimensional imaginary time evolution. Okay. And so if that's the step that's like a miracle occurs and it turns into your Monte Carlo. It's like you're sampling you're sampling this sum here, which includes samples of alpha. So this might be one example. Maybe spin up, spin down, spin up, spin down, blah, blah, blah. That could be an alpha state. And then that particular whirl line configuration somehow corresponds to how these Hamiltonian operators evolve that basis state. And in order to be ergodic, you have to construct a sampling scheme that samples all possible alphas and all possible whirl lines. Okay? So somehow this part here will turn into your Wx. I meant to do that. Questions on this?
So a configuration is a specific sequence of n states?
Yeah, so you'll also sample this number n.
Right.
Yeah. So you'll have n operators in there, and that n will fluctuate. If you have an ergodic algorithm, you should be able to sample some distribution of those n's also. Yeah.
But the sign?
Yeah, so the sign's what I'll talk about, I guess, right now. Why not, right? So before I get to the sign, anything else?
Formally I understand this, but why do you want to do this?
Well, so let's do,
Like if you can
yeah.
do the exponential, you have the exponential and you do.
Well, you can't do the sum, just like you can't.
Like the first line, I guess, on that one. This thing, Wx.
This, why do you want to do this?
I think he's saying, why don't you do the thing that's more familiar to most people, just do a Trotter competition, right? Because you get a minus m.
Yeah.
Oh, I see, yeah. So this has no Trotter error associated with it. That's why I like doing it. So you can also do the Trotter decomposition and have some delta tau squared error, right? Because you have an approximation. But we don't use that type of QMC, Trotter decompositions for most of these spin models that I'm going to talk about.
You're saying you have an error when you just test time.
Yeah. Whereas here you don't. Here you have to be careful to sample you usually have some distribution of n that contributes to a partition function, and you just have to make sure that you sample that entire distribution, basically. So
And that's like doing the summation.
yeah, So the miracle occurs is taking this basically formally correct expression and figuring out how to sample, like how to construct weights and how to sample those sums. And so you're sampling, basis state configurations, all these operators that occur, the power of n that occurs. And basically once you do that, if you can do that sampling, then you've constructed your Monte Carlo. So I think this is the simplest. I think it's simpler than doing a Trotter error. I don't know, a Trotter decomposition, and this is more sort of like the current state of the art for how we would do spin simulations. All right, so the sign's the big thing here. So remember we have a detail balance. We have a transition probability. So we're trying to construct a transition between maybe two types of world line states. And we have to make sure that the ratio of weights is positive. So we have Wx and Wy, or whatever I wrote last lecture. Right, so that ratio has to always be positive in order to construct a transition probability, which is P, x goes to y, that's positive. And if it's not positive, you can't interpret it as a probability, and you can't do Monte Carlo on it, just basically by definition. So every one of these, okay, so the problem occurs in these matrix elements. If you have matrix elements that are the wrong sign, and actually there's a sign that occurs here. So one way to basically think about the sign is to take this minus in front of the beta, which occurs n times, and just write that product of matrix elements, alpha naught, with the sign associated with each one. Minus h alpha n. Okay, and if I can make each one of these matrix elements positive, then it doesn't matter what my Wx and Wy is. That ratio will always be positive. And then I can interpret that as a probability, a transition probability. So one of the first challenges of constructing a QMC is to make this happen, is to basically take all these matrix elements and make sure that every single one of them is positive. Okay, that's sort of the conventional way of doing it anyway. I want to start doing an example, or this just is too abstract. Okay, so let's do a Heisenberg model. Spin 1/2. It's not entirely obvious, but I mean, there's different ways of taking this Hamiltonian and constructing a configuration, right? X. But as you can almost imagine there, you have to have operators that you take from this whole sum of operators and just sample maybe local operators individually to move these world lines. Okay. So we're going to break up the Heisenberg Hamiltonian into its diagonal and off-diagonal pieces. So we have to choose a basis then, right? So we'll choose alpha to be SZ. Ups, downs. We'll represent it like that. And then what we want to, in this d plus one dimensional expansion, we want to sample operators, both diagonal, so SZ or SZ, and off-diagonal operators, which evolve this state in imaginary time. Okay? And that choice is basically up to you. When you're writing a Monte Carlo, you can decide how you take that Hamiltonian and break it up and basically calculate these matrix elements. Okay, and there's many different ways to do it, and it depends on, maybe you have other terms in this Hamiltonian, and so on. So this is really the art in the state of the art. So diagonal terms, so we can imagine sampling terms that are like, I'll write the basis state in a minute, but minus j sz sc. And you can write all the matrix elements out. You might have up, or you might have up, down, and so on. So let me write two of them. Okay, they're diagonal. All you're doing is, so s dot s, I guess this is 1/2. So you have something like minus j by 4, and right, these have the opposite sign. So you see right away that if you constructed a weight, or if you constructed a configuration that had diagonal matrix elements from this Hamiltonian, you would get a mix of both positive and negative terms. So it looks like you have a sign problem right away. Right? You can imagine, if I have some scheme that takes a whirl line and inserts or removes a diagonal operator, and a whirl line again is maybe just tracing these upspins through imaginary time, then that update asking whether or not I want to insert or remove a diagonal operator, like, could it easily just put in minus signs? So how would you get rid of this minus sign, or this sign problem? Pardon? I think that's basically the point of what you're doing with the sampling the sums. So I don't know if you can exponentiate that and save yourself. Right, yeah. Just add a constant to the Hamiltonian. Right, so right away, here's your first sign problem, man. It's like, you solved it. Nobel Prize coming. So like number of, so I've implicitly taken my Hamiltonian and broken it into bond terms, and I can imagine sampling these bond terms. So maybe number of bonds times some constant. If you add that to the Hamiltonian, and you need C to be maybe greater than or equal to j by 4, then you could make this, this matrix element 0, and you can make this one j by 4 plus j by 4, say. And all that's affected is your energy in the end. So you have this constant that you've added to the Hamiltonian. If you take the expectation value of the Hamiltonian to calculate the energy, you'll just be off by this value that you've added. Okay, does that make sense? So again, I haven't told you how to construct the updates. The updates have to be constructed via detailed balance. But the simplest one to think about is like adding and removing like diagonal terms. So your simulation, I'll draw one in a minute. I just want to do the off-diagonal operator first. But your simulation cell would be this, say, basis state, evolved in imaginary time. And then you could, with detailed balance, construct transition probabilities for inserting and removing this. So if you have this constant, you won't have the sign problem. You'll have all positive transition amplitudes. Okay? So more seriously, if you wanted to sample off-diagonal terms in this basis, number one, you'd have to use your imagination to construct maybe moves to do this in this higher dimensional space. But let's just focus on the sign for now. So I'll basically have matrix elements that look something like this. And I've written them in a way that they operate or they evolve this alpha that I've chosen. You'll get a minus sign here. And if you had down, up, up, down, you basically get the same matrix element. So that's an off-diagonal term. It has a minus sign in it. And so, there's again the chance that you'll get the sign problem, because in this way of trying to combat the sign problem by just making all of these up top there, all these matrix elements individually positive, this minus sign has been uncancelled. So if I insert a single off-diagonal operator, just like in the diagonal case, I'd be inserting and removing minus signs. But in this case, you can't just add a constant. You can't just add number of bonds times some constant to fix that sign problem. So it's more serious. So let's look at how we might fix that sign problem. So let me draw this full D plus one dimensional configuration that I'm calling WX. Okay, let me up spins are X's, down spins are O's. I probably have something like this in the lecture notes, which are on the website, by the way. So Okay, so here's my alpha naught. I have to evolve this with operators, and I'm sampling again both this configuration and the operators in imaginary time. And I'm choosing to break these operators up as bond operators. So let me draw them like this, because they're objects with that locally take 2 spins. And maybe this is a diagonal term. And I'll draw the off-diagonal term with some other color. There's no blue left. Thanks, Leon. Here's some green. So here's my off-diagonal operator. And so I construct a simulation cell that looks something like this. Here I've inserted an off-diagonal operator. Oops, so I flip these spins. And let me put one more layer on this. So I'm going to have an n equals 3. But remember that I want to be periodic in imaginary time for this finite temperature simulation cell. So I'm going to have one more off-diagonal sorry, I missed. One more off-diagonal operator here, which flips that spin pair back to its original configuration. Right, and this is alpha n equals alpha naught. Okay, so this thing here is a very simple, very rough picture of a d plus 1 dimensional configuration. Alpha naught, alpha 1, alpha 2, alpha 3. And they're all supposed to be lined up. Okay, so you see a couple things here. You see that, again, you know, off-diagonal operators in this case have to be used to make the world line. So the world line that I drew over there is just sort of an abstraction of maybe, you know, the time evolution of these x's. So in this formulation, you have to have off-diagonal operators such that these world lines are periodic in imaginary time. These two are simple, they just go straight through. Okay, so this simulation cell that I drew is sort of like, I didn't say it, but it's sort of implicitly one-dimensional. So it's like 1 plus 1. And so if I want to take my world line and keep it periodic in imaginary time, then I'll always need, you know, an even number of these green off-diagonal operators in my expansion. Okay, and so it looks like I'm fine in terms of the sign problem there, right? Because I have this sign here. There's a minus sign for every single one of these operators, which is contributing to my weight. But there's always an even number. So it's like I have minus 1 to the n, and n is even. Okay, this thing's been taken care of with a constant, and there's always an even number. So this is the essence to solving the sign problem, really, in this type of Monte Carlo. If the number of off-diagonal operators is always even, then there's no sign problem. And then your ratio of wx to w, I don't know, y or whatever I called it, will always be interpreted as a probability. And so you can learn a lot from this type of picture, actually. So this is sort of implicitly always true in one dimension. But now you can ask, well, what if I had a higher dimensional lattice, right? So what if this layer, this alpha naught layer, was some two-dimensional lattice, and I wanted to simulate the Heisenberg Hamiltonian on it? So basically, you have to worry about the same thing. You have to worry about whether or not you always have an even number of off-diagonal operators. So let's think about maybe 2D squared.
I have a question.
Yo.
This means an even number throughout the entire configuration, right?
Right.
You have to act on the same sites.
Yeah, so all that matters is that sign, right? So in one dimension, they have to act on the exact two same sites.
So
right? So, but you can have other ones in other places in the simulation cell.
So why would it be any different on the square for a 2D lattice?
Yeah, good question. So you can have, so imagine this path. Maybe I'll just isolate one square, okay? And I have a d plus one dimensional, I'm putting, let's just look at the off-diagonal operators. So maybe I have spin up here, and everything else is spin down. So what's the best way to draw this? So there's two ways that this world line, which is coming up here, can remain periodic. Oh my God, man. Okay, well, so I can imagine putting an off-diagonal operator, which I think was green, somehow operating between, I don't know how to draw it really now, but operating between these two bonds. So I have a green operator in there somehow. So I flip that, I flip those two spins, or if this is bosonic, I hop a boson over. So somewhere up higher in imaginary time, this world line now progresses up here. I have to have another off-diagonal operator. Let me draw it like this. That brings these back. And then my world line's periodic. So there's always two. But you don't have to have operated on just that bond. You could have kept that world line periodic by moving this, here, here, and then here. So that's the idea. All right. So alternatively, when this world line came up, kinked over like this, it's gonna be hard to draw. So I'm here now. So I could have moved it here, oops, here, here, and then back here. Okay, so that would have been an operator here, here, and then I don't know, here. I don't know why I'm drawing the operators now. Okay, so I have one green operator down here, and I have 1, 2, 3 more, so it's even, right? So if you look at all possible loops on the square lattice, all possible paths that you can take that spin up, then you'll see on the square lattice that you always need an even number of operators in your d plus 1 dimension to return your world line to being periodic. Does that make sense?
Why do you only draw single operators? Isn't the WX involved in the whole Hamiltonian?
Right, so I've chosen at some point to only sample individual bond operators. So individual, this defines bonds. So I've chosen just to sample individual bond operators. And I have to make sure that my Monte Carlo updating procedure is ergodic in all possible bond operators in order to get the proper Hamiltonian in here. So it's just a choice. And I could have made a different choice. Okay.
So just to clarify, alpha naught and alpha n are by definition always the same.
If you're doing a finite temperature, okay, yeah, so if you're writing your partition function like this, then it has to be a diagonal matrix element. Okay, it doesn't always have to be the same, but I want to keep it the same for now because I think this is a nice sort of geometric demonstration of the sign problem.
So when you have a one-dimensional system with a periodic boundary condition with an odd number of sides, you still have, now you can have an odd number of flip operators getting you back to the same thing.
Oh, that's a good question, yeah. So if your spatial boundary is like periodic, you're saying, and in principle you can get one, you can get a sign problem from that one path, yeah. And that sign problem should go down. It should get smaller and smaller, right, as you go to the thermodynamic limit. But yeah, in this way of looking at it, yeah, you would have to worry about that.
Do you always have
No, I purposely did an anti-ferromagnetic Heisenberg Hamiltonian. Okay, if that was a ferromagnetic Hamiltonian, no problem. You wouldn't even think about it. Every term would just have a positive sign after. There's a negative sign here, right? So every one of those would cancel. Yeah, and I'll talk about that. Yeah. So this is exactly you're seeing the point is that you can mix the signs, and if you mix the signs such that all the minus signs occur in the diagonal part of your Hamiltonian, then you can always get rid of that sign problem in a trivial way. So it's only the signs that remain in the off-diagonal part of your Hamiltonian that you really have to think about.
So what do you do on a triangular ladder?
Yeah, good question. It's like I'm planting questions here. It's perfect. So if you have a triangular lattice, right, so let me just, if I redid the whole thing triangular, I'll just do it real sloppy like. Right, so there's two possibilities. One is that you have an operator here and then another operator on the same bond. So that takes your whirl line, moves it back. That's an even number. It's 2. But you can also have another path that's, so here moves to here, moves to here, moves to here. Right, and that's 1, 2, I don't know, 3. So that's an odd number. Did I do that right? Right. So here you're going to have, even, odd. Here you're mixing even and oddness in your and there's other paths, of course, right? There's other paths that you could have taken this world line that could have even or could have odd numbers of hops in them. So whenever you have that type of situation where you're mixing together even and odd numbers of possible paths, that's what you would conventionally call the sign problem. And there's no solution to that. That's why Heisenberg model on the triangular or Kagame lattice aren't solved with quantum Monte Carlo.
So for the square lattice here, this was because the particular Hamiltonian we're looking at only has negative off-diagonal.
Right, I did that on purpose, yeah.
Okay.
Yeah, same. So this would be also, this is the same Hamiltonian here. This would be the same, anti-ferromagnetic Heisenberg. That would have the sign problem.
Okay, but there's no reason to be guaranteed that a 2D square for some other Hamiltonian would solve this sign problem, because some of these off-diagonal terms could be negative. So.
Yeah, you can have other off-diagonal terms. Right, yeah. So it has both to do with the operators that are off-diagonal and the geometry of the lattice. Yeah, it's not just everything on square doesn't have the sign problem. That's not true. You can easily construct an off-diagonal operator that gives you a sign problem on this square lattice.
Yeah, so, if you simulate, let's say, spins,
Mm-hmm.
they're in a sense distinguishable by their sites. So then you have to go back to the alpha 0 and alpha have to be the same.
Mm-hmm.
Let's say you were simulating particles like bosons, they at time infinite.
Like itinerant bosons, you mean?
You could have permutations because let's say your representation is coordinate representation of each of n particles, and then many body state with a symmetric combination. So then it seems like.
And you're talking itinerant bosons somehow in the continuum?
Bosons,
yeah.
So then the alpha n really can be a permutation of bosons.
And so the updates are really complicated in that type of Monte Carlo. It's called pathing row Monte Carlo in the continuum. And you do get sign problems in that case. You get very serious sign problems there too. So I think one of the points is it's really easy to get a sign problem. And I definitely, in these path integral Monte Carlo for itinerant systems, you get tons of sign problems. Yeah. Nothing. But can you sample the configurations ergodically? Those two questions are the same. They're one and the same. I could, instead of using a bond operator, I could use bigger and bigger objects. I could use plaquettes or triangles, plaquettes, and blah, blah, blah. And so at some point, that typically affects your ergodicity. And as you go to that limit, your ergodicity goes to like 0 somehow. So.
Isn't it also that those states get kind of less and less computable, like the eigenstates?
Yeah, okay, that's a good point too. Yeah. Yeah, so you have this exponential problem that why are you using Monte Carlo, which I never talked about. Yeah.
There's some kind of physical property that corresponds to Hamiltonian being sign problem free, or is it just
It's a good question.
solve like one Monte Carlo doesn't mean anything?
So I mean, maybe you're interested in whether or not certain states of matter can only be represented with Hamiltonian instead of a sign problem. I think I mean, my guess is that's probably not true, but people definitely believe otherwise. So I'm going to talk about spin liquids, and spin liquids is the thing you should be thinking about. Can I construct, a Hamiltonian that doesn't have the sign problem but has the interesting maybe spin liquid or topological phase that I'm looking for? That's an open question.
Are there situations in which the sign problem is basis dependent?
Of course. Yeah. It's highly basis dependent. So part of solving the sign problem is maybe finding a basis, right? So if you can find a basis where all the problems get into the diagonal terms, right, then you don't have a sign problem anymore in the conventional sense. Yeah. So that's what some people. Okay. So another way to look at this that's not geometric is the so-called Marshall sign rule. Or the Marshall sign construction. What the Marshall sign construction is actually just doing a basis rotation. So you have your off-diagonal operators. You have your, say, Heisenberg Hamiltonian on different lattices. So on the square lattice, the formal way to look at this type of idea is to just do a basis rotation on one of your sublattices. So you have A and B. And I have this written in the notes. So you basically do a basis rotation. It's a unitary operator. T. So you're rotating your spin basis by, I guess it's pi by 2 around the z-axis, around the z-axis. On, say, one sublattice only, on the A sublattice only. And you'll see if you do that basis rotation that every term that looks like, minus, s plus, s minus, s plus, through that basis rotation, because, the bond operators go between sublattice A and B, that you'll get rid of that sign. So it'll be a plus there, AB. So formally, that's the procedure that is equivalent to this. And the point is a basis rotation like that doesn't exist on non-bipartite lattices. Okay, so that's why, that's really the Marshall sign rule, okay? So the Marshall sign rule says that, square, simple cubic, any bipartite lattice, you can basically solve that type of Hamiltonian. But triangular, Kagame, pyrochlore, any of these lattices, you're not going to be able to do this basis rotation. Hamiltonians that satisfy this I don't know why I wrote that all. But sign problems that can be made, Hamiltonians that can be made sign problem free via this procedure are sometimes called stochastic. I can't believe I'm saying this. And they're called stochastic because it's like stochastic with quantum. Really. By the quantum information community. And so the quantum information people, specifically Barbara Turhal and Sergei Brave, they've done a lot of work on so-called stochastic Hamiltonians. So one of the sort of motivations behind, quantum computing is whether or not you can build a quantum computer that can simulate non-stochastic Hamiltonians, right? Because you have this basically exponentially bad sign problem that occurs if things are non-stochastic. So stochasticity is a property that is related to some complexity classes in like complexity theory for quantum computation. QMA complete, quantum Merlin Arthur complete. It's like the the analogy of NP complete problems for classical computers.
Do you need the Hamiltonians that don't have a sign problem on one of these problematic lattices or
So this Hamiltonian on the square lattice is stochastic. This Hamiltonian on the Kagame lattice is non-stochastic. Sure. Well, your Hamiltonian defines your lattice. The nearest neighbor, that defines your lattice, right? So, yeah, it's just semantics, but yeah, you're right. This procedure whereby all matrix elements are made positive. There's other ways of combating the sign problem that I'm not going to talk about. So for example, there's other bases you can choose. You can do this type of simulation in what's called the valence bond basis, which is like the actual singlets up, down, minus down, up. You can choose that basis, and it looks different. The way that the sign problem is solved looks different. In many cases, it's equivalent. You can map it to this stochasticity issue, but actually there's some non-trivial examples where that type of basis solves a sign problem. And one of them was done by Julia Wildeboer, who's here. Where are you, Julia? Yeah. So she showed that you can sample the RVB wave function, okay, nearest neighbor singlets, on a Kagame lattice in that basis through some trick called, Pfaffian quantum Monte Carlo. And that is, you calculate the Pfaffian, which calculates all the dimer coverings. And you can do that in some way that doesn't give you the sign problem. But it's not this procedure, so I would still call that non-stochastic in some sense. Determinantal Monte Carlo, half filling it, the Hubbard model, this type of thing, that's also non-stochastic. That solution to the sign problem is a different philosophy, basically.
I guess that gets at the question I wanted to ask a little bit. So it sounds like this notion of stochasticity.
Yeah.
Kind of basis dependent.
Sure.
So
Yeah.
You really are only looking at certain unitary rotations on certain sites. Is that?
They would call it stochastic in that basis. Yeah. So you'd say this is stochastic in some basis, as far as I understand. I don't know how that relates to QMA complete and everything,
I'm
but
surprised that it relates to things like that, which might be more. Yes, it might be more invariant.
I'm also surprised. I mean, it's like, is there a basis transformation that solves the antiferromagnetic Heisenberg model on the triangular lattice? That's, I think, in some sense, why that's a huge problem, right? There's some Hamiltonians which you might think are non-stochastic that maybe you just haven't found this basis rotation for. And then you would say, okay, actually, this is stochastic, which is equivalent of saying, oh, this problem we thought was NP complete, but now it's calculatable in polynomial time, right? It doesn't mean that it's a general solution, so it's not solving this NPP problem, but you can always maybe hope that there's some specific solutions to that problem. So I think that's kind of the idea. It's like you have an NP complete problem, and you might find specific instances where you do this basis rotation and turn it into a polynomial time problem.
Are there cases you can just live with the sign problem, just use very large computational power?
Yeah, so the way you usually live with it, let's see if I can do this. So you have weights which are positive. Or sorry, weights which are negative. That's your sign problem. But you can imagine taking that sign out of the weights. Sine of x maybe. And then having the absolute value here. SIGN x wx. And you can imagine sampling in that modified ensemble where the weights are all positive. And then what you have to calculate is like, the expectation value of this thing and the sine over the average sine. So you can try that. And in general, that gives you a variance that blows up exponentially with your system size and with imaginary time, the size of imaginary time. So this is the standard sort of thing that people do. Yeah. Other questions? So the question, okay, so Kagame lattice, antiferromagnetic Heisenberg model, probably Steve White's going to talk about it. And all the progress on that model has been done without QMC. DMRG, two-dimensional DMRG, tensor networks, all sorts of stuff like that. So you might wonder, are all spin liquid candidates sign problematic? Okay, like are they all non-stochastic? So that's a good question, and I think it's something that's worth thinking about. Are all quantum spin liquids non? And the answer is no. End of lecture. No. Now the answer is no, but with some caveats. So I've written examples in the notes of Hamiltonians that are I guess I don't know, I can't quit using that word now, that are stochastic but also have spin liquid states. And there's basically broad classes of these types of Hamiltonians. So one class of Hamiltonian is the so-called BFG models, Balance, Fisher, Girvin. And these are models that are Hamiltonians that are U1 invariant. Okay, so they have some U1 symmetry. And they realize Z2 spin liquid phases, which are quantum spin liquids in the same class as the toric code that Leon talked about. I have a Hamiltonian here to write down. Let me make sure I don't screw it up. So these are on the Kagame lattice, which is cool. Lattice of corner sharing triangles. And they consist of two terms. One called a cluster charging term, which I don't know who named that. I think it was Yonbek Kim. So I'll write like this. A diagonal term plus an off-diagonal term. H naught parameterized by V. So I'll say sum over all hexagons, SZ hexagon squared, where SZ around a hexagon is the sum of all I in the hexagon. Let me write it like that. SZI. Okay, that's ugly. I blame Leon. It's ugly but necessary, maybe. And what this classical term does, just like we talked about last time, is it promotes, if you just had this term in the Hamiltonian, just H naught, it would promote a degenerate manifold of equal energy states, right? And these states would be ones where every hexagon has, 3 up, 3 down, okay, or something like that. So. I only have 2 hexagons. Oh, I have one here. I could keep going if I wanted to. So my x's are my spins up. Okay, so that it would just be the one element of the highly degenerate extensive manifold of states that satisfy the classical part of the Hamiltonian. And it's generally a good philosophy to take these states and then perturb them with a quantum term. Because just like in the toric code, you have like a loop structure, and then you basically have an off-diagonal term that gives you a superposition of all possible loop states or something like that. So you can imagine an off-diagonal term that would do something similar here. And actually, just looking directly at the spin states, I can imagine taking a hexagon, a bow tie, and making an off-diagonal term in the Hamiltonian that just takes, spin up on the corner of the bow tie and move it like that. And that term, if I wrote it out, and it's written out in the notes, would be an off-diagonal term. I can make it such that the sign in front of it is negative. Okay, well, I might as well I'll write another one. But so it's stochastic in the sense that all off-diagonal elements cancel the minus signs in the d+1 dimensional expansion. But this thing would promote a Z2 spin liquid state, the analogy of the toric code. So So you can almost imagine that these kinetic terms basically operate all over on this highly degenerate manifold, and you know, it's zero temperature, right, and move you in between all of these different equal energy states, making it a sort of quantum superposition state. There's so from this type of idea, this very simple picture, there's many Hamiltonians that are sign problem free in this same class, which promote, you know, at some, you know, you V and K or something, at some ratio of couplings, a transition to a Z2 spin liquid state. Even if your H1 was a nearest neighbor XY term, ferromagnetic, that would be enough to do it. So I think that's a really nice model. So if I had H equals H naught plus, no, 1 minus, right? So that sign cancels. Say T or J. I think that one doesn't, but I forget now. It's a good question. Roderick Mosner studied these, didn't he? But I'm not sure he studied actually with the charge clustering. Yeah. Do you know the answer? Because I don't. Yeah. Well, so just like this one, this term here, which works, like 2 of these terms give you one of those terms. Like a transverse field, 2 transverse field terms will give you this term, right? So perturbatively, you basically build up your off-diagonal pieces. Yeah, so.
I know it works for Carlo.
Oh, yeah. Yeah, so that's a good point, yeah. That'd be neat. Yeah, so transverse field Ising models are also stochastic, typically, as long as the sign's in the charge coupling. Yeah, there you go. There's some homework for you guys. What? No? What about a term like that? So this one's nice in a sense. It's like you can see how 2 of these hopping terms, if you will, or 2 of these terms give you one of those. So in second order in perturbation theory or something like that, you get that type of term. But this term will also promote, you know, you'll basically promote you can promote a defect, a charge defect, if I move this thing over here. Right, so I can promote a charge defect here because I have 2, and here because I have 4. And those are my deconfined E's, right, my electric excitations in the toric code. Additional hopping moves would move these 2 blue charges, you know, away from each other. This is non-local because if you want an isolated one of these, you have to move this one via this type of hopping all the way to infinity and so on. Okay, so again, the sign in front here is what makes this thing sign problem free or stochastic in this type of picture. So it's a very simple case. You know, it's very simple to do a quantum Monte Carlo in some sense.
You think, but for small t, you're saying it's okay to add that term?
There's no sign problem. You can have large t here.
No, but for large t, you might leave the phase. Like
Oh yeah, sorry, yeah. Large t, you'll have a superfluid for in plane XY. Yeah, good point. So you'll have a phase transition. You'll basically have you'll have a phase transition. So a phase diagram that looks like, what do I want? V over t or something like that. For large V, you'll have a Z2 liquid phase. Then you'll have a Koster-Salas transition into a superfluid or an in-plane XY, phase. And then that critical point will be deconfined in some sense. It's called XY star. It's because you have these charges, these fractional charges condensing. Yeah, so there's lots of rich phenomena in these types of models that you can study with QMC. Speaking of pyrochlore, you could also study the spin ice, the classical spin ice Hamiltonian that I introduced last time. 2 corner sharing tetrahedra. I could have a Hamiltonian that just has a, antiferromagnetic term around the 4 spins of every tetrahedra. SESZ. So the sign in front of that term is sign problematic in principle, except we'll be diagonal in the SZ basis, so we just add a constant and get rid of it. And remember we talked about square ice, right? So there's some mapping from this. You want, 2 spins on each tetrahedron. And you can map this to an arrow on the dual lattice now. I mean, square was dual to square last time, so it was easy. But a dot might be an outward pointing arrow, maybe from an up-facing tetrahedra, and an inward pointing arrow from a downward-facing tetrahedra, because a dual lattice is bipartite. So you get this arrangement of like electric fields, like we did for the squarized case. And I think the simplest term to add here is actually this hopping term. I'm thinking of bosons when I call it hopping, but. And as Mike and Leon and Matthew and other people showed, actually a simulation, quantum Monte Carlo was done on this type of model. This promotes this three-dimensional U1 spin liquid that we kind of discussed a little bit last time on Friday. So here you have examples of, two-dimensional, sign problem-free Hamiltonians that harbor Z2 spin liquids, three-dimensional, sign problem-free that harbor U1 spin liquids. What these Hamiltonians all have in common is they're, again, U1 symmetric. I don't know of any case where you have an SU2 invariant spin model that has a sign problem. Oh, sorry, that has a spin liquid without the sign problem. With a quantum spin liquid without. Does anyone know? Or maybe that type of sign problem that can be easily solved. Okay, so there are candidate spin liquid phases on some maybe SU2 invariant Hubbard models and so on that have different solutions to the sign problem. But something like a Kagame lattice, Heisenberg type, anti-Fermi Heisenberg type picture, I think we still don't know if there's any sign problem free models that have interesting spin liquid phases. This is a Sandro Sorella's theorem that they don't exist. Sign problem free models in SU2 invariant Hamiltonians that promote spin liquid phases. Questions?
Is it theorem or conjecture?
It's a conjecture. It's interesting, it's an interesting problem. Lots of people maybe believe that. I mean, just because they're so difficult to find. Okay, so let me move on. Let me move away from the sign problem. What I knew I wasn't going to have time to talk about was ergodicity. But ergodicity and solving ergodicity, or making updates that are ergodic, once you've solved the sign problem, can actually be very challenging. So don't downplay or don't think that ergodicity doesn't matter. There's very many sign problem-free Hamiltonians that you don't see quantum Monte Carlo simulations performed on because people can't basically derive ergodic updates. What about the toric code that Leon wrote down? Since we coordinated our lectures so well. Does that have a sign problem? If you look at that Hamiltonian now that he wrote. No sign problem, right? Both terms of minus signs in front, both the plaquette and the star term or whatever. But do you see a lot of quantum Monte Carlo work on toric codes with perturbations, finite temperature, and so on? The answer is no. And the reason is you can't derive or design sort of ergodic updates for the say two-dimensional toric code Hamiltonian. So that's a good example. If you do this type of picture, d+1 dimensions, you start putting in star and plaquette operators, star, plaquette, and then start to think about how you would ergodically simulate, all the different configurations of stars and plaquettes decomposed in this way. You'll find that it's like nobody solved that problem. So there's no sign problem, but I don't know what you call this problem, an ergodicity problem or an update problem. Taking your configuration X to Y it's not known how to do that in a simple way. That's a good question. I mean, the loop gas is defined in the SZ basis, isn't it? Right? So, I mean, you have loops that are. Why am I drawing loops? There's a small loop. Is that right? Yeah, I think so. So you can imagine that's your loop, and then the off-diagonal term is moving around those loops, say, right? So the gauge term that I talked about last time, would move. I think that's the basis you want to think about. But like I say, as far as I know, like essentially just doing that calculation with this type of Monte Carlo idea has never been done. People add other terms of the Hamiltonian. This is fairly recent. I think there's been Japanese groups do this that add other terms of the Hamiltonian that move you away from being a pure toric code. And then you can ergodically sample these other terms that occur, but then you have to take some limit when those go to 0 and so on. So that's, you can imagine adding bond terms or something like that, and then taking some limit and hoping you stay in the same phase and stuff like that. So ergodicity is a big deal. I'm not going to talk about it because I want to talk about something else. But
Since you talk about ergodicity.
Okay, I'll talk about it.
Well, can you just elaborate a little bit? I don't really understand why. Maybe it's related to the previous question. Like, why can you not? I mean, suppose you just did the boneheaded way of just generating spin configurations and with Boltzmann weight.
Yeah, but there's no Boltzmann weight anymore, right? So the weight is this sum of all your vertices that occur in this d+1 dimension, so this expansion dimension.
You mean the stochastic?
Yeah. Yeah, so the thing the weight is proportional to all these matrix elements, which is this thing, right? So the weight this is the weight. There's no Boltzmann weight. I mean,
okay.
you have beta in there, but it's not a Boltzmann weight in the classical sense. I mean, it's and not in the way that you're sampling it. So you have to somehow, take this thing and turn it into a, maybe take away this operator, or add this operator, or take away this operator, and that's, and maybe you have world lines which are all these loops would form world loops, which move up in this extra dimension. And so you need something that sort of takes those loops, those world lines that are loops, and move those things around without breaking them. So you need membrane updates or something like that to do it. You have to move this membrane. Ideas are out there, but I think basically implementing stuff like that is difficult.
If you did Trotter.
Trotter there might be possibility in some other scheme. So the classic example of non-ergodicity, if we just go back to sort of the Heisenberg type picture where we have world lines that are, they look like that. The idea of how do you insert more off-diagonal operators in here? You basically have to take maybe a line like this and kink it out with 2 off-diagonal operators. Like that would sample the world line. You can do this. You can find pairs of diagonal operators that are adjacent in imaginary time, or and then do this kinking and unkinking procedure. And it's mostly ergodic. This is the old way people used to do these types of algorithms. But actually, it doesn't sample something very important. It doesn't sample the winding number sector. So the superfluidity, or the spin stiffness, is measured in world lines that wind around the periodic boundaries in space like that. And you can imagine that doing this thing of identifying kind of operators that are adjacent to each other and replacing them with diagonal off-diagonal operators doesn't do this. So what you could construct a simulation and you would always get 0 for the spin stiffness. Or in an XY model, the superfluid density, if you want to call it that. So there's an ergodicity issue. And that was only really solved in the 90s by Everts and Prokofiev and Sandvig and these people. So even it seems fairly recent, but this type of sampling is I think, this is really the problem that we work on. The sign problem you can almost right away figure out if you have a sign problem. It takes like 10 minutes. And then the rest of the problem is trying to figure out how to construct these sort of updates. So it is a big, it's a big field, if you will, and that's why we get paid the big bucks. So I'm going to move away from ergodicity. Just be aware of it. Don't come to me with a Hamiltonian. Look, there's 5 terms. 5 bond Hamiltonian. There's no sign problem. Can you do QMC? Because really, a lot of issues with ergodicity occur in these types of Hamiltonians. Not to discourage you, but you should definitely. This is why, instead of just talking about software packages, I think we're giving these types of lectures, right? Understanding world line Monte Carlo right from the basic ideas That's what's going to let guys like you come up with the new innovations, I think, the new types of algorithms and so on. So I think especially in the case of Monte Carlo, these things are very simple to code. It's worth thinking about these types of algorithmic issues. I want to go on to a measurement in my last 10 minutes. And I want to measure the proper Renyi entanglement. Am I doing this right? Trace. The proper Renyi entanglement entropy that I sort of did the classical analogy of on Friday. And the reason these measurements are particularly important for spin liquids is because, as Leon was alluding to, you identify spin liquid phases via their entanglement properties. There's one way to identify spin liquid phases. There's other, you can look at correlation functions and so on, various quantities, but directly looking at something like the topological entanglement entropy in a quantum Monte Carlo, that would be sort of a smoking gun identification of a spin liquid phase. And it's been done for these sort of BFG models, and Julia's done it for these Pfaffian Monte Carlo simulations of RVB wave functions. But other models like these pyrochlore models with these U1 liquids, people haven't really explored much what goes on in the entanglement entropy there. So there's a lot of open questions with entanglement entropy. All right, I'm going to do a quick and dirty derivation of this measurement for the second Renyi entropy. So remember last time I had two replicas, and the configurations, the classical configurations were constrained in replica A, and in replica B they were free. Okay, so that philosophy of sampling that modified partition function is going to translate here, but I'm going to do it a little bit different. So imagine I have a D+1 dimensional simulation cell, and I'm going to do something confusing, just to confuse you, and that's I'm going to throw away the periodicity condition, and I'm going to say I just want to converge this thing to the ground state. So remember I said you can make your imaginary time, make your beta huge, and then the world lines, basically, I'm not going to care about this boundary once you converge into the ground state. The ground state is what you should be thinking about, of course, when you're looking for quantum spin liquids, right? So let me imagine that this object is, my partition function now is basically an inner product of a ground state wave function. And I want to calculate some observable in the ground state. Oh, bad notation. Like that, okay? And I can construct a quantum Monte Carlo called a projector, QMC. J? I'm going to say J. Which is just like the SSE sort of, but you strip away all this finite temperature nonsense. And just imagine that you have world lines living in D+1. But you don't have periodic boundaries anymore. The way you define this type of simulation cell is just by applying a large power of a Hamiltonian to some basis state, which is a trial basis state. So you can imagine this like this is what a variational Monte Carlo looks like essentially. Large power of the Hamiltonian applied to some alpha, and I'm going to project inwards. And it looks the same as the SSE in the sense that I have all these matrix elements, resolution of the identity, and so on. And what I should get out if I do this correctly, when n is infinite, if I've arranged this Hamiltonian such that the ground state energy eigenvalue is the largest in magnitude, I'll get something like this. Okay, and a limit when m goes to infinity. So m is, it was like n. I called it n before. N is like the power that you're in the Hamiltonian. So let me just imagine I've thrown away all that finite temperature formalism and I've constructed this basis or this configuration. Okay. Have you seen this before? The power method. This is what Lanczos is based on. You do a power method in it's called a Krylov subspace. You project out the ground state and the first excited state and so on. So this type of thing this philosophy is very common in numerics. The center slice now is where all the action takes place. I'm not periodic in imaginary time, but what I've done is I've taken my alpha and I have all these Hamiltonian terms, and here's my ground state wave function. And I have another projection happening from the other end. I project to the ground state. And there's my partition function. It looks just like the partition function at finite temperature, essentially. Okay? Okay, so let me take this ground state wave function, right? And I want to derive an operator that I'm going to measure the expectation value of the operator, and it's going to give me the second or third or fourth Renyi entropy. Okay? And to do this, I'm going to do a proof in this sort of Penrose notation. It's what they use in tensor networks, so it's tensor network notation. They've renamed it tensor network notation. And maybe Steve White will talk about tensor networks in this language, who knows? This might be useful for you tomorrow. So let me imagine my quantum Monte Carlo gives me a ground state wave function. I'm listening.
How is what you wrote related to the Renyi entropy though?
That's what I'm deriving. Yeah, I'm going to use this. I'm going to use this idea that I can simulate a ground state via some projector method to calculate a Renyi entropy. That's what I'm doing here, okay? So, question, where does Renyi come from? Okay. So I have this thing, and I have two of them. Maybe I have two projectors, and I'm forming an inner product, which gives me what I call Z. And let me call this something like this in this tensor network notation. Typically what this means, this object, is that you have a vector. And this represents the index that goes through all your Hilbert space. And when people talk about tensor networks and mirrors and all this type of stuff, they have different objects. You might have a matrix that has two indices, right? Matrix. A scalar has none. And you can form tensors and all sorts of things, right? But I just want to start with a vector. That's my ground state. But I want to do something that is important for the entropies, the entanglement entropies, and that's subdivide my indices into, my elements, my basis, into those occurring in region A and those occurring in region B. So I'm going to imagine doing this bipartition in space. Okay. So the way I'm really going to write this is with two indices, but don't get it confused with a matrix when Steve White starts talking about matrices. I just want one for A. What color is that? Orange. And one for B. Okay. Anyone confused yet? I got confused at this stage when I started doing this. Now I'm going to form various objects. I'm going to form a density matrix, which is an outer product. Okay. So density matrix in this notation is just that bad boy with indices like this. What I can do is I can trace over, the reason I've split the indices up is I can trace over like degrees of freedom associated with one region. So my reduced density matrix is really just a trace over B. And in this notation, a trace means you can track these indices. So I do something like this. And that's my reduced density matrix. It's a matrix now in the sense that there's two free indices. Okay. And it's an operator that operates on the Hilbert space associated with A only, the subregion A, right? So now you see where this is going. Rho A squared. I gotta do matrix multiplication. So I need two of these reduced density matrices. I've contracted B. My A's are free, but I have to do a matrix multiplication. So there's my matrix multiplication there. And the final step to make this look like that formula for this Renyi entropy, or the second Renyi entropy at least, is to take a trace over B, right? No, sorry, trace over A. This trace here is a trace over the remaining space. So trace over A of rho A squared. Okay, so okay, now that's a scalar quantity. Does that make sense? Now what I'm going to do is I'm going to untie this object a little bit. I'm going to, it's going to be topologically the same thing, but I want to take this triangle and move it down here. And I'm going to take this triangle and move it down here. Okay, so that's equal to something that looks like this. Oh no, I want to do the other ones, sorry. I want to keep these ones. I'm going to move this one down here and this one down here. Okay. So this one it must look like this, right? I did it backwards. Okay. So this is a different object. But what it looks like to me is on the left-hand side, you have a tensor product of two ground state wave functions. And what you've done is you've applied some operator that switches the indices of region B. And we call that a swap operator. And all that swap operator is this thing. Okay, it takes all your basis states, takes all the states of your system in region B and swaps them between two replicas. So you have two replicas, just like you did in the classical case. Replicas. And in the ground state, the entanglement entropy of A is the entanglement entropy of B. So this is also equal to the expectation value of swap A, which is what I wanted to derive, but I did the wrong one. Okay, how'd you like that derivation? So if you replicate your simulation cell like this, you make two of them, the middle's special, you divide yourself into region A and B spatially. So here's A, here's B. Oh, whatever, did it backwards. You insert a swap operator in the center slice on both replicas. And your world line, which is, looks like this in region B. In region A, when it hits the swap operator, it comes out in the other replica. And if you simulate this system and you calculate the expectation value of that type of world line topology, you'll get the second Renyi entropy after you take minus log. And the second Renyi entropy is, for all intents and purposes, as good as the von Neumann entropy, especially for detecting things like topological order in a Z2 spin liquid or something like that. Questions? You guys are disturbingly quiet. Did I do something wrong? Well, it depends on your basis, but the way it looks depends on your basis. The measurement's basis independent, so the result of the measurement, but the picture I drew below with the world line, that's what it actually looks like. So I've going from this to that on 3 chalkboards maybe isn't completely rigorous, but that's all the steps you need basically in whatever sort of basis you're working in to derive the way the swap operator would look in quantum Monte Carlo.
So do you see that we're allowed to move these vectors around in two-dimensional space where we
Yep. Insert auto resolution is identity. You have your basis state moving up. What happens is when you hit the center slice, which means you're in your ground state, what you want to do is you want to swap basis states between the two ground state, the replicas in the ground state, sorry. And so that's what you've done there is you've swapped the basis state between replicas. So the rest of the world line isn't affected by the swap operator. It's only that at that one point where you basically do that. And that's what this means here in some sense. The indice associated with this replica gets moved down and contracted with the index associated with the other replica.
But the replicas are just these two copies. That's what you mean, the two replicas?
So I might have said that wrong, but I would call these two replicas.
But in this picture, it's just the up until middle section and beyond the middle section. That's the two replicas.
This is one replica.
That's one.
This is just one representation of a usual partition function. That's why I have just 0 here. But here in my replicated case, I have 0 cross 0, or whatever this thing's called.
You simulate two systems?
Yeah, you literally take two systems and you just tie them together in the middle like that. That's how the first second Rennie measurements were done. I just want to do the finite temperature derivation. It'll just take me like 1 minute. So. Yeah.
So the point of this middle part was that
So in practice, you take it. It's finite, but it's converged. You have to take m until ground state properties converge. So the way you do this in a Monte Carlo is you would measure the second Rennie entropy and then increase m until nothing changes, and then you actually operate on a fixed size. But let's go back to the finite temperature version, since that's leads into what I want to finish with. In the finite temperature version, which you might want this Rennie entropy as a function of temperature. You have A and B. Spatially, you have two replicas. But now, you're periodic in imaginary time. So this picture that I so carefully constructed is now the original SSE picture, or the original world line picture, where these are periodic. So all your world lines are periodic. So especially in region B, that's simple to draw. Here's periodic world lines. Oops, that was a close one. Now, if I want the second Rennie entropy, I want to insert that swap operator, but I'm translationally invariant in imaginary time. So what do I do with it? I just put it at the top here, or wherever. And all I do is, again, it's translationally invariant. So if I have a world line coming up, and it hits this bad boy here, it just comes out at the other replica, but now I'm periodic in imaginary time. So it moves down here, and has to hit the swap operator such that it comes out back here again. Okay, so just the topology at the boundaries of imaginary time is all that's really different in between finite temperature and 0 temperature. And so actually what's going on, remember at finite temperature, this is each size beta. So really what I'm doing here is I'm taking a simulation cell and in region A, my world lines are periodic with 2 beta, but in region B, I'm periodic just with beta each. And if you shrunk these down to just 2 layers, that's exactly the picture I had derived classically last time. Right? So all I've done is I've included a quantum extra dimension, and this thing I think I called Z prime or something like that. So the second Rennie entropy is basically just minus log of this modified multi-sheeted Riemann surface, Z prime. You just got to be careful to normalize it by Z squared. And then the same issues I talked about last time, calculating these free energies and so on with integrations have to be done here.
So in this picture, we don't care about it going merging to the ground.
Right, because this quantity is well defined at finite temperature. So maybe it's not of interest for, say, 2-dimensional Z2 spin liquids where I think you want to project the ground state precisely. But say you wanted to measure the finite temperature entanglement entropy of a Heisenberg model or whatever, transverse field Ising model at finite, something with a finite temperature transition, look at a critical point, who knows, right? This is the finite temperature version. So, again, all you have to do is, again, I went through it fast, just like last time, but all you would do in a quantum Monte Carlo is do this non-trivial topology, this replicated topology, and calculate the free energy through some thermodynamic integration, and also subtract off the regular free energy, and you'll have a second Rennie entropy. If you do this for one of these BFG models, you'll get an area law minus the proper topological entanglement entropy, that's log 2. If you do it in a UN spin liquid, I have no idea what you get. You get something that, it's gapless, so you get something that depends on the shape of the region, all the aspect ratios of the region. There might be universal numbers in there, but I think we don't know what they are. You can look at critical points. So there's some theory about moving through, I talked about this XY star critical point. If you move through that critical point, you get contributions to universal numbers that come out of the entanglement entropy that have to do with this, these spin-ons condensing and so on. So there's a whole rich, I think, world of interesting physics. But I think the simplest to understand maybe is the sort of topological entanglement entropy. And it's accessible with just precisely this thing. So that's all I really wanted to say. Spin liquids, they do occur in models without the sign problem. Okay, so even if you're non-stochastic, you can get spin liquids in certain cases. Worry about ergodicity, not just sign problems. Okay, like the 2D torque code, no ergodic algorithms exist for that. And all these measurements and stuff, sign problems, this all involve, Monte Carlo is very simple to code. And there's a lot of innovation in the algorithms. So I think guys like you, the next generation, coming up, I think you could do a lot of interesting stuff. So okay, that's all I have to say. Thanks.
So just a general question about this SSD. So it's important to go over all ends, but you have to put some sort of truncation in the end. So how does your truncation affect it?
Right, so I didn't talk about that much, but usually what you do is you have all your n operators, and then you also have identity operators that you throw in imaginary time, which pushes your simulation cell bigger than, say, the specific n that you're sampling. And you can fluctuate inside of this sort of extra space that you've made for yourself. And what you do is you always just make sure that you have enough space to fit any number of n that you want. So that there's some distribution, there's a tail. You just make sure you sample that entire tail, and as long as you're big enough, you'll do that without any error at all.
The first thing you do is formulate a high temperature expansion.
It looks like a high temperature expansion, but it's not perturbative in beta. Right, but as I said, what you do is you make sure that you get all n. And of course you can't, at some point it becomes impractical. Same here. At some point it may become impractical to actually converge these things. Right, so at some point you might not be able to sample world lines ergodically if your m or your n is bajillions, right? And that's just a limitation of Monte Carlo. That's a finite size limitation essentially in imaginary time. So you finite, you have scaling in number of sites in your lattice and also in beta.
One of these model Hamiltonians, like the sign tree, I never got much of any problem.
Yeah, so physically and models like that, you have no problem effectively reaching the ground state. Yeah, which is why we use these things. I mean, there's nothing a priori telling you that that's the case, but that is the case for most models. Although, some more complicated Hamiltonians, you might look at that one with the cluster charging, and you might wonder if you're really converging out the ground state because the algorithms are more complicated. So you have to be careful. You have to do it systematically as a function of size, basically.
Sorry, so if you take a finite n in the end, how is this different from a property composition with some very small delta?
Well, they should both converge to the same thing. So if your delta tau is small enough, yeah, that delta tau squared error you get should go to 0. There is no, missing n error for what the thing I did. So there is no additional convergence that you have to worry about. You just have to make sure that your simulation cells are big enough. So if you have delta tau, if you have a Trotter step, you typically take a finite delta tau and then you do another smaller delta tau and so on, and you converge everything in that delta tau for a given fixed temperature. Here you take a fixed temperature and you make you just make sure that you always get all n's that are part of that distribution, and you'll know if you don't, because you can basically just keep track of that. And so there is no delta tau error in that sense. But there still might be a limit to the beta that you can do. Okay. Who's chairing this thing? Can we go for lunch? No.
I'm sure. I think it's a good practice.
All right, thanks.
I just want to
to remind whoever is interested that I will be with this and see if you like to do it at 4 p.m. If you're interested, stick around after the end of the last lecture.
Hey, buddy.
The rhetorical godicity, map it